Okay, so good morning, everybody. It is a pleasure to have the incomparable Dominic Gold, who most of you know already for being one of our former graduate students, and whose image is still lingering on posters around the department. So thank you very much for agreeing to give this talk. And today you're going to talk about, I suppose, deterministic random bit generators in cryptography. So the floor is yours, with all ears. Thank you very much.
Great, amazing. Thanks so much. Yeah, so I'll be talking today about something that I think is somewhat taken for granted in cryptography, but is actually very important, which is the concept of random. Like, random as a concept is incredibly important in cryptography. And I'll sort of be giving you a rundown. Oh, sorry, it flipped over. My plan for today is to explain how is random used in cryptography, and then how do we generate it, and then I'll be going over a particular mechanism which is known as deterministic random bit generators, also known as pseudo-random number generators. They go by both terms in the literature. And then I'll show you just sort of a pipeline. Go over approved constructions, approved in the NIST context, I mean. And then we'll talk about some of those and one particular example that warrants a little bit of extra introspection. So what is randomness used for, right? So I think when we think, if you like read any cryptographic protocol, especially things in instantiating cryptography or like even creating communication channels, something that's really important is the concept of random. You know, just to give you some examples, random is used in key generation, right? If you look at, sorry?
Stop. Mute.
Oh, okay. Yeah. So random is used in key generation. When you create cryptographic keys, you need random. And alternatively, random itself can be used as a cryptographic key. Look at AES. It's like, right, you can just use the random on its own as a cryptographic key. Another place where it can be used is things like initialization vectors. So that way, initialization vectors. So what I mean by that is when you start a protocol, you want something so that if you have to repeat this communication channel, it's not exactly repeatable. So that way, it's not subject to a repeat attack. In the same vein, I'll include nonces here. They're kind of one and the same. So nonces means numbers used only once, and that's really useful because that way someone cannot repeat what you did. And if the nonce is a different nonce, then it's not going to ever turn out the same thing. And then one last sort of application is salted hashes, right? So to ensure that after you hash something, it's a little bit different each time, you add a little salt to it, you sprinkle some random in there, and then then you get a different output. So these are all really important use cases of random in cryptography. I think there's sort of like two natural branching questions that come out of this. Is one, how is it generated? How generated, right? How do you actually generate random to use in these protocols? That's like vein of question number one. And then another like vein of questions is how do you measure, or rather, I'll just say this. I'll just tell you, you want good random, right? If you're saying you have that's sort of one of those things where you can quantify it, but you have to be careful because if you have a string of all zeros and then you randomly put a 1, in some sense that's random because you randomly put a 1, but overall, statistically, most of that is zeros. So that's actually bad, right? So we want to be able to somehow quantify what is a good amount of random. Let's start with this guy first. So good random. So the way we measure random, like the metric we use to measure how much random we have, is something known as entropy, right? So entropy is a measurement you can assign to basically a bunch of bits. We'll just use bits here. I understand that you can turn, they can come out as bytes, they can come out as hexadecimal, they can come out as numbers. I'll just use bits just to make it zeros and ones. So entropy, right, is a measure that between 0 to 1. And 0 means you have no entropy. Everything is completely 100% predictable, and so and there's no it's completely predictable. So all zeros, a string of all zeros or a string of all ones or zeros and ones alternating, anything like that has a predictability element to it is going to have very low entropy. Versus 1, it means it has a high amount of entropy. It's like you can't tell if the next bit is going to be 0 or 1, right? So there's a couple different measures. I will go over just 2 very briefly. I won't go into any details, but you can read up on this if you'd like. The 2 main measures of entropy you'll see is a concept of Shannon entropy. And then the one that I've been researching the most recently, which is the concept of min entropy. So basically the main reason that I sort of in practice prefer this one. Why do I like this one so much? Because this one has a nice property that if you have multiple bit strings with different levels of min entropy, you can basically combine them through concatenation, and then the min entropies add up together. So that's the nice property about that specific metric right there. Shannon entropy does not necessarily follow that. So, but these are just different measures you can use to calculate it. But the most important part is 0 means low. So this is a low value, and this is a high value. That's the most important things here. So that's how we measure entropy. And then, so that answers okay, that's how I know I have good entropy. But how do I actually generate random with good entropy, right? So there's a couple different ways. I would say that there's 3 that I can really collapse to 2. So the first one is nature. Nature is just naturally chaotic, right? Like if you just took what is Cloudflare? Oh yeah, Cloudflare uses the lava lamps, right? That's what they use. They use that as their random number generator, basically. Or radiation from the sun, or temperature fluctuation, but very, very high amount of significant digits, temperature fluctuations over here in the very least significant bits. Those are very random, and you can use those as a source of randomness. The next one is, I'll call this physically, or rather, I'll call it hardware generated. I'll call that hardware. So what do I mean by hardware? What I mean is literally you have a chip, or you have something that has electrical signals that is effectively random. So the most famous example of a hardware random number generator is based off of the concept of ring oscillators, which is basically you have an odd number of NOT gates, and that is pretty random. That's impossible to model, basically. So you have ring oscillators. And then the one that I will be talking about, which is pseudo-random. Random. So what do I mean by pseudo-random? What I mean by pseudo-random is that it uses an algorithm to produce your random values for you. So what that means is you have this is basically uses some algorithm, and we'll talk more about that. But this is the concept. So this guy here is very interesting, because what you do with a pseudo-random number generator is basically you need to have a little bit above that. So you have a pseudo-random number generator. Let's think of it like a black box construction. You have your we'll call this your DRBG, deterministic random bit generator. So actually, sorry, let me put that here, DRBG. Yeah, in the literature, depending if you read the NIST standards, they'll call it a DRBG. If you read academic literature, they call it a PRNG. So that's like kind of confusing, and that took me a bit to like make sense in my mind. I'm going to use DRBG because that's what I've been using at work. So if you have your DRBG, then inside of your DRBG is effectively what we call a random, we call this a seed. So this is a seed value, and this seed value itself comes upstairs from, you have noise. So you have some type of source that you pull from to create a seed. And the seed is sort of like this value that gets fed into an algorithm. I'll go over what those are in a moment. But with that algorithm and seed value, you can just start spitting out random. You can just start spitting random out. So this just gives you random. So here's like a black box construction of what a DRBG kind of looks like. So I think, so we're a room of cryptographers and but also more importantly, mathematicians. So this is something that I had to ask myself. So if you look at this picture, this is sort of the question that was my very first question when I started learning about this subject. Why? If you have a random source already that you use to feed in as your seed, then why do you just not hook into that random source as your random output? In other words, why is there this in-between layer between the noise source and your random? Why just not make your noise source as your random? So that's something that took me a bit of time to, and I hope that's like, if that's it's a question you had, it's a very natural question actually. So why would you ever use this construction? So the next question is why? Oh, but before I go with that, are there any questions on like the concept of taking something, seeding an algorithm with that value and using it to produce more random? Is there any questions on like this construction or anything else I've gone over? I'm happy to answer now. Yes, hello.
Thank you for giving the talk. What's the full name of DRBG?
Deterministic random bit generator.
Thank you. I have one question.
Yes.
Like, why do we really need to do it in this way and not just a coin toss and just store it? Like, why do we really need a pseudo-random number generator?
That coin toss you just talked about, let me ask you this. Who's doing the coin toss? Is it a computer or is it a person? Let me throw it back to you. So, the computer? Then the computer is in a sense doing this. It needs to have a concept of a Bernoulli distribution, right?
Yes.
Okay, then your computer's flipping it, but your computer abides by the laws of physics in the sense that it has computer hardware. Is it doing an algorithm to flip that coin?
Yes.
Then there you go. There's your DRBG.
I see. Okay. Makes sense.
Right? Like the fact that you're simulating that coin toss in software in your computer is a deterministic random bit generator in the sense that there's something going on in there that you don't see, or maybe you can see, but you don't see the internal state that's flipping that coin for you.
I see. Okay.
Good. Okay, great. So why would you ever want to do this? Like again, so I think the question fundamentally is you have a noise source. Why would one not just use that as your random? A couple of reasons. One is and this is potentially the number one most convincing one, is efficiency. These algorithms produce random very, very, very fast. But this can be so I'll say this can be fast once you have a seed, and this can be very slow. So if you hook directly into the random noise source, you're going to have to wait a while to get another random output. And when I say a while, I'm talking in the order of potentially seconds, but for certain cryptographic applications, that can be too slow. Like I'm talking about like real-time calculations. DRBGs are fast, right? So efficiency is like reason number one. I'll say efficiency / speed because I kind of think of those hand in hand, really. The next thing is that you have a tractable internal state. So these algorithms are state machines, basically. So they can keep track of the state of what they're in. They're like, I produced output 1,327. You can like record that, is what I'm trying to tell you. Versus with a noise source, you would have to have a pretty robust logging system in order to get your nature-driven or physical noise source to be logged like that. These DRBGs, they have an internal state. So really the seed kind of lives in another state box like this in some sense. And the other thing in here is like a ledger that keeps track of everything. The nice third reason is that it's platform agnostic in the sense that the algorithm is platform agnostic. But clearly what's not platform agnostic here is the input, the noise, right? That does need to be tailored around the thing. But the algorithm itself is platform agnostic. So in a sense, this is no weirder than using the noise available on the system you're using. And then the last one, which is a good, because now a lot of my job at my lab is a lot of T&E, so testing and evaluation, is that deterministic is good for testing. So good for testing. If it's deterministic and everything is exactly the same all the time, then you can make sure your thing works by repeating and making sure that nothing is going weird. So it's good for testing. So this is not really a math reason. This is more of like a actual engineering reason, which I don't do the engineering. I have the people do that. I just make sure the math's okay. So speaking of though, this potentially number 4 should be one of those things where it's like, okay, if it's good for testing because it's repeatable, isn't that a vulnerability? Because then that allows for certain attacks, repeat attacks, right? So here's like a question that I again had is isn't deterministic like almost in a sense antithetical to random? Like this is like a question that I had to think about for a bit too. Why are we okay with this? Because it's deterministic. I thought I want random, right? That feels wrong. And the answer is because, you know, the noise source you're basing it off of is itself not modelable. That's what makes it random, is that you can't model it. Things are only random because you cannot model them. And so the seed you're instantiating the DRBG with comes from that noise source still. So in a sense, the noise you're pulling from is not modelable. The seed you pull is also not modelable. So even though the DRBG uses a deterministic algorithm, the thing it's basing it off of, you have no way to model. So it's still random. That's what I'm trying to say. So this is in fact, still random as noise is random. That's sort of the like lesson with this. So I hope I've done a decent job of convincing you that DRBGs have a place because of certain efficiency, and also that they're not redundant to the goal of producing random. So this is the basic construction. And so where do you like learn more about this? In some sense, like I said, there's academic literature, like they're called PRNGs in the literature. But the place that I've been doing a lot of learning myself is the NIST 890. You have it's like a suite. So A is sort of like the overall, hey, here's what these things are, here's the approved algorithm. So I'll sort of say A, so you have 90A, 90B, 90C. A is approved constructions. I'll call B like entropy, and more entropy. Like that's, they're like, you know, hey, gotta measure it, right? And then C is basically how you make A and B meet in the middle and kiss. It's like, okay, so you have this construction that takes in randomness and can produce more, that can produce random. B says, here's how you measure a good input to put into that thing. And C is like, okay, now make up and stop fighting. So C is like, put it all together. I would say only read these if you're really bored, because this is like 500 to 600 pages of documentation. And I'm saying documentation. It's not an academic paper. This is documentation about these. And it sort of tells you like how to do each of them. And so I kind of want to say an interesting sort of historical thing about specifically this guy. So why does this one exist? B is an interesting sort of reason it exists. So what B has in store is it tells you, hey, here's how you can calculate the entropy of your inputs. And I recently learned that this is mostly historically driven rather than any mathematical derivation, which is basically that when everyone was starting this line of research, when this research started, making random numbers, what was everybody's first thought? Everyone's first thought was, let's analyze the output of the random generator and do statistical tests to see if it's random. And basically what everyone sort of came to the conclusion is that this is useless. As yes, it is actually kind of hard to statistically tell something is purely random on its own. Like that the output of a DRBG is random. So then they shifted and said, okay, let's check if the input is good. And if the input is good, and then the output's good, we're going to trust, and the output doesn't throw some insane red flag, then we're going to trust, then this thing is good. So they shifted from looking at the output result here, which you still do, that's actually in the 822 tests, but they shifted up to the input and said, let's check if the input is reasonable and that it has high entropy. And the reason entropy is such like a huge talking point is because cryptographically, you actually need very, very little deviation from full entropy, so 1, to have a cryptographic advantage over an adversary. You don't need that much, really. If your thing is just a little bit biased in some way, then you actually have certain properties that give you, I'll say, cryptographic advantage. So that's what you get, actually. So yeah, so these are like the suite of tools. And so A introduces what I'll call 3 DRBGs that NIST and NSA have approved and said, yes, you must use this. I think their wording is actually like shall, SHALL. And it's bolded. That's actually the key word. It's bolded, which means you must do this. So shall with a bold means you must do this or else we will not certify your thing as compliant and then you cannot use it in national security. That's actually what that means. So what are the 3? You have hash-based, and then you have block cipher-based. So the 2 and under hash-based are 1, of course, a hash DRBG. Why did I capitalize? Hash. And 2 is a hash message authentication DRBG. So these are the 2 approved ones under NIST. And then block ciphers, the one that's approved is I'll use 3, like 3. The one approved under block cipher is a counter-based DRBG. So this is like AES block cipher stuff. You can read it if you'd like. So these 3 DRBG constructions, this references the internal algorithm. So if I go back to my little picture here, I sort of draw like a little algorithm box. Alg. A-L. Okay. G. Okay, that's gonna have to work. So there's like a little algorithm box there which these 3 refer to. So that's the difference. And these enjoy really nice properties, security properties. property number one, so I'll say that there are two major security properties that you really want in this thing. Security property.
Dominic?
Yes.
Just a question. These three that you are there modes or like modes of operation or are they instantiated with particular?
Yeah, they're different instantiations in the internal algorithm that's used to produce random. So what I mean is that you can like swap this component out, this algorithm component out right here with a different algorithm, but not on the fly. As in when you make the software or whatever that uses this, you have to implement one of those three if you want to be NIST compliant.
Yeah, but are they implemented with a particular, say the block cipher, are they implemented with a
Oh,
particular
yes, I'm
cipher,
sorry. Yeah, so they're implemented depending on the implementation instantiation details are dependent on the security strength that you instantiate with, whatever your lambda is. So your security strength determines the input parameters. And then from there, that actually also influences how much noise you have to pull to start making randomness down. So it's all based off your security strength. If whatever you set your security strength to, that influences everything else downstream.
As underlying block cipher, for instance, you would use AES or what?
Yeah, use AES, it'd be AES 256.
Okay.
Mm-hmm. So the security properties that these enjoy is the first one is prediction resistance. And then the second one is backtracking resistance. So in a sense, what are these about? These basically cover the scenario that someone has captured your seed or internal state. Because I think it's not too hard to see in this picture that the security of this construction is like, you can like reduce it down to the security of your seed. That like the seed is the most important part of this construction. If your seed is exposed, it's over, right? Because imagine an adversary can capture that seed value. They're like, I don't care about the noise source. I don't care. I'm going to capture your seed that you got from the noise. They slot that in their own DRBG using, and then they have like three separate ones, one for each algorithm. And now they can start matching your random with one of the three. If they can match your random, it's over for you, right? Because imagine, for example, one of the secret things you did was you XORed a random value to a key. Imagine that's your secret sauce. Then they only need to have their three parallel DRBGs. They took your seed, they put it in there. They have three values, they XOR, and now they have one of those three will match your random. And then it XOR it with that thing, and then it's back. You now recover the secret key, right? So the seed is the most important part of this construction. So these security guarantees are about if seed is compromised. So it's the scenario that your seed has been compromised. So let's start with the one that I think is a little bit easiest to understand, which is backtracking resistance. So backtracking resistance says if your seed is compromised, you have the guarantee that all previous outputs until that point, until compromise, still look random. So all the previous outputs, just because I recovered the current state, it doesn't mean I can backtrack my way to all the previous values you had, is what I'm trying to say. So this one comes, so you get this guarantee by adding in additional inputs. So that is, you have like some personal ID string, or you have some nonce that you got from the random as well. But this one is basically some math guarantees. So I'll call this math guarantees from additional inputs. That's how you get this. Like you get this you get this from having additional certain inputs, and the math shows that yes, you're fine if that works. Prediction resistance is probably the more interesting one. So this says if the seed is compromised, future outputs are not predictable. So this one is conceptually from what I just said earlier. If the seed is compromised, then you're screwed. Like someone can use that seed to predict all future outputs in your algorithm. So how do you possibly achieve prediction resistance? Well, it's kind of like, what's the lowest common denominator here? The answer is just, make a new seed. This is called the reseeding operation. So reseeding is enforced, whether it's a enough time has passed, you must reseed, or whether it's you've done 1,000 calls, you must reseed. That is something in that it has to be done. But basically, you reseed frequently enough, and you'll get this. This is more of so in a sense, I think of one as implementation security, and one is a mathematical security, right? They come from different places. So this has been a lot of you can read all of this in the standard, right? You could go to the NIST standards and read all of this. It's not too hard. Something that I think was very interesting is going to be talking about that there was actually a fourth DRBG here. And I think the cryptographers in the room will know what I'm referring to. But there was a fourth DRBG that is no longer in the standard for very good reason. That is dual EC DRBG. So I'm going to assume that certain people in the room know what I'm talking about, but if you don't know what I'm talking about, this is a random bit generator that used elliptic curves to generate random, right? And basically the idea behind this one is that, yeah, you have public P and Q, and you do elliptic curve stuff to start generating random points. That's no problem. So I actually want to talk about this in detail for a bit, because you're going to see what it looks like when what does an attack look like on such a construction, right? So let's talk about why it's no longer in the standard. So dual EC DRBG, I'm going to sort of explain it two ways. I'll explain it in here is a circuit diagram, and then here is a very easy to read algorithmic construction of it. So basically the way I think of it is you have some state. Oh, sorry. Let's do it better. Let's do it public parameters. So you have elliptic curve points P and Q, and I believe that this is selected from P256. So that's a public elliptic curve that you can just look up if you want. It's an elliptic curve. It's a well-defined elliptic curve by NSA, I believe. So you have some public parameters, some point on the elliptic curve P and Q. And effectively what you do is you have an internal state, and then you update this state through taking the x coordinate of this guy times point P. So you multiply it times P, and then you take the x coordinate. This is some intermediary step Ri. So let's start with this. And so we'll split this into two halves. There's the state update, which means, okay, you've changed the state, now update it. So we'll do that part first. So state update says the new state is the x coordinate of Ri times P, times P. And that becomes this becomes I plus 1 now in some sense. So Si plus 1. Yep. So this is the state update step. And then what's the output update? The actual output you get out of this random number generator is the x coordinate of Ri times Q, the other elliptic curve point. And then you just take the least significant bits of this guy. So this is the protocol that was implemented in the NIST standards for this. So is there any sort of question? Sorry, so let me just do a little bit more demarcation. So this is called our state update. This is our actual generation step. Random generation. And then, yep, and then this is the, yeah, so this is perfect. So are there any questions on how this?
I have one question.
Yes.
So why is the security only considered when the key is compromised and not for like uncompromised key? Like, is there any notion of security? Like, how do we define the entropy of these constructions?
So we define the entropy. So the entropy is done for the input. The reality, and this is like a cold stone truth, is that if you have an input with really low entropy, so that's your seed, and you run it through one of these algorithms, if you calculate the entropy of the output, it's going to tell you it's 1, because these algorithms are generally pretty good. Like in a sense, imagine you take this string of all zeros and you hashed it. If you calculate the entropy of that, it's gonna be pretty high actually, even though the string of all zeros is very low entropy. It's like 0 entropy technically. So you can't calculate the entropy from the output. You have to calculate the entropy before you put it in. So that's 1. And 2, there's no key here in a sense. But there is secret information, and the secret information is the seed that you used to start your to initialize your DRBG. And so the security is just a matter of like, in a sense, if your seed is not compromised, everything's working great. And an adversary, generally speaking, although we're going to get into this in a moment, so hold the phone, cannot recover your seed from the output, then the only security that you have to worry about is if the seed is somehow exposed or someone can take it. Right. So and also, of course, this in implementation world is surrounded by a cryptographic boundary module that a software engineer has to actually come in and make sure is like completely compliant. There are certain things in the security world that I know I don't think about at all. So for example, there are things in security where they explicitly tell you that this color wire and this color wire have to be at least 3 millimeters apart, like things like that level of security. So there's an implementation security, and then there's also the if this is revealed, what can I do to recover? That's the 2 types of securities that we're considering in these constructions.
And like one more question. So like how do generally the constructions there might be very complicated, right? Like how do you generally calculate the entropy, like doing statistical analysis, or there is like some hardcore distribution function that you can actually compute for these constructions?
Right. Okay. Yes. You calculate. So I'll give you a math answer and then I'll give you a real world answer. Okay. Yes. Math answer is yes. You can do what you just said. All of the stuff you said is solid. I have no problem with doing either. You can do a bunch of statistical tests. You can make sure things look uniformly random. You can look at the PDF. You can look at the CDF, all of that stuff. Real world answer is NIST has implemented the suite of 90B tools on their GitLab. It is like 15 tests. It takes like an hour to run on a megabyte of data. Go run it. Like it's code. You go gather your data, put it in a file, and then feed it into there, and they will tell you the entropy.
Okay, so it's like a calculator. Just you give the output and it gives you something.
What's the difference between a calculator and a well-formed statistical test that has lots of knowledge about the underlying true distribution of the data?
What's the name of that software that you can use to test the random numbers?
890B is the documentation. You can go online and find NIST has published a GitLab that has those tests in there.
Okay.
Okay, great. So this is the model of the dual EC DRBG construction. And the reason I bring this up is because in general, this isn't one of the fastest constructions, but it works. It does the job. You're not going to have a problem doing this. However, there is something that there is something built into this that we need to we'll do a little understanding, right? So let's assume one knows. I just want to make sure that this is clear. This is the output. So this is literally the output of random. So imagine an attacker, they can capture this. That's fair game, right? An attacker should be able and should be allowed to capture the output of your black box construction. This is Cryptanalysis 101. So they can capture that, no issue. And also the input, right? So we have a somewhat active attacker. So assume that one knows the D such that D times Q is equal to P. In other words, the discrete log, scalar multiple, whatever between P and Q. You know that these were chosen in a way that one is a scalar multiple of the other, right? So this is now, you don't have to implement it that way. I'm just trying to say there's no reason to believe P and Q are multiples. But if they were, you get a very interesting thing going on here. So if it is known that this is the case, then you can actually, my claim is you can recover the internal state from output alone. So this clearly violates a level of security, right? The fact that I can recover the internal state, which is the beating heart of this system, through the outputs alone is a large vulnerability. So I'm going to show you, I'll try to convince you, and if I don't convince you, I'm sorry, but we'll give it a try. So how can you do this if you know the scalar multiple, right? So first of all, we'll say, so I guess proof, but I'll put sketch. So remember that we know we can get let's call this TI, is the least significant bits of the X coordinate of Ri times Q. So I'm just calling the output here T sub I for right now, right? So pretend we know we have this. Then I can, for pad in the range 0 to 2 to the 16 minus 1. So remember, it's we have the least significant bits. So if this is 256 bits, I'll just put some numbers to this. If this is 256 bits, then this output is 240 bits. So we just throw away the bottom 16. So what I'm trying to say, so we do some throwing away. That's the construction, okay? I didn't choose that. That's the construction. So we're going to go through those 16 bits that we threw away. And then we're going to say, for each pad here, we're going to compute the concatenation of that pad to Ti. In other words, we're adding them back. We're going to exhaust through everything you could have possibly thrown away, right? It's 2 to the 16 things, and add it back, and then concatenate it back to your Ti. Why does this? Why am I going to do this? Because if I multiply this by D, then something here will align with the previous state that it was before. So in other words, something here will become this guy, right? The Ri times Q. So Ri times D times, so let me just make sure the math works out. So something here will have become that. So it'll be pad of that is times D. Yep, times Q. And then D times Q is P, which is exactly, let me just make sure. So SI is Q. So that's times Q. And then I multiply it by D. Oh, yep. Okay, cool. So this becomes Ri times D times Q, which is, so this guy is P right here. 1 second, let me just make sure this is all right. So, oh yes, and and Ri itself is already Si times P. So what you get this way is you get, yeah, there's something going on with the indices here that I need to fix. But basically, at the end of the day, you get Si times P, and I don't think it's P squared. I think I must have written something wrong up here. But the point I'm trying to say, oh no, this is good. I'm sorry, I'm wrong. This is just Ri times P. I'm good now. Why does this work? Take a look at this, and let's go back to the update step. So if I just take the X coordinate of this product, I get back the updated state in the loop. So an attacker can just go through all possible things you threw out. They're taking in your trash, and they knew how much you threw away. And then based off of that, they can recover the internal state so long as they know that P and Q are a scalar multiple of each other. And so you say something, you're like, Dominic, why would an attacker know that P and Q are scalar multiples of each other? And what I'll say is, you're right, an attacker could never know that, but the person who gave you the points P and Q to choose to instantiate your DRBG might know that, and might have intentionally done that on purpose. So in other words, with a bad initialization, that's what I'm trying to go back to over here, by the way, right? With bad initialization, you can actually have no security guarantees, and in fact, have complete compromise of your system because your seed value, your state value, is completely revealed through outputs alone. So here's an example of such a construction, right? So this right here shows you that if from output alone, I can iterate over 2 to the 16 things, and I get back the internal state of my DRBG, and therefore no security guarantees. Actually, in fact, no, like none at all. Okay, great. So so from here, you really can just, so what does the implications? The implications is that I can now forever match your random with this. I now have one of your states. I now know what it is. And if you don't reseed, okay, that's fine. I will match your random forever. And if you do reseed, I'm just going to repeat this one more time. I'm going to do exactly what I did again. So in a sense, this entire step is iterable. So iterate. Frequently to account for DRBG reseed. And there we go. So yeah, so that's so there's some math there. I didn't want to make this all like just standards and going through standards and stuff like that. But yeah, here's some interesting math. So if you wonder why is dual EC no longer included in the thing, I don't want to say anything definitive, especially because I work for defense now. But here is a potential motivation for why this construction is no longer included in the NIST standards, because if one were to happen to know that the scalar multiple between those 2 points, you can always recover the internal state, and you are completely screwed. You're compromised. Okay, thank you. That's my talk. Yeah, I'm happy to have any questions.
Dominic, I have a kind of thinking of, is there a like you could find out a countermeasure to that attack if you use an elliptic curve where you have a pairing, then you can easily ensure that P and Q are not multiples of each other.
Right. So I'm trying to say this as carefully as possible. What if the person who told you to use this gave you P and Q?
Yeah, but I mean, if you have a pairing, then if you calculate the Weil pairing of P and Q and you find something which is non-zero, then you know that P and Q are not multiple of each other. Without so you have a mathematical certainty that
I hear you, Francesco. I'm saying if someone says, I will not stamp your document and let you use this unless you use this P and Q.
Well, I mean, like if you use if you are on an elliptic curve and then with a pairing, and then you find that the pairing of P and Q is 1, then yes, of course.
Right. I agree with you. Anyone can choose P and Q, and as long as it doesn't have this property, you're safe. Actually, you are secure. I'm saying
what I mean is that even if they give you P and Q, you can look as say as an initial measure, as an initialization measure. Just say like check with the pairing that the pairing is not 1, and then this would basically assure you that P and Q are not multiple of each other. So basically the fix would be to take an elliptic curve which has a pairing, and then to have as an initialization part to just calculate the pairing of P and Q. And then if it's not 1, then you know that Q is not a multiple of P.
Listen, I understand what you're saying. This is a policy thing. This is not math. I'm telling you that this is a policy.
Why isn't such a...
I have to be. I'll let you read up on it. Like, read up on the history. This is a crazy history. If you want to read up why this was removed, there is a very good reason that that people had to use this construction, and then there's a very good reason why within the first few years you had cryptographers from all around the world that were saying that this is a bad construction for this very reason. And it's no longer a math question, it's a policy question of people in very high power telling you you must do it exactly this way, or we're not allowing you to use cryptography.
Well, of course, if they force you to use some specific curve, then you actually lose trust because they...
And why do you think it's not in the standard anymore?
Okay.
I have one question.
Yeah.
So, are there any implications of side channels on the way the implementations are done?
Oh, yeah, absolutely. Right. So there are side channel attacks that exist on these things. And in some sense, I haven't looked deeply enough at them. But I know I've been cited a few papers by my colleagues for me to read about and to potentially implement. But yes, there are side channel attacks. The ones that I have found the most interesting that I've read up on is things that, like, mathematically, you know, in some sense have very little weight, but in an implementation standpoint are super relevant. So literally, like, if you could measure the temperature of the computer while it's doing stuff like this, could that give you information about stuff? Things like, or like, if you had the passive ability to just read certain bits, there's actually certain things you can get as well. So there are side channel attacks in this state update process and the random generation process that do reveal information. I have to look more into that, but you're right, there are theirs. Mm-hmm.
Yeah. Okay. Thanks.
I have another question, just
Yeah.
on what do you call the entropy here?
Yes.
So is there something, because so if something is deterministic, right, it has entropy 0 normally, right? Theoretically, because it's because of the very nature of because of its very deterministic nature, right?
Mm-hmm.
But so is there something like a computational entropy which has been introduced? So something where you say, okay, like in a polynomial time, then the entropy basically where the entropy would be a function of time. Like if you run it polynomial, like on a polynomial.
I see. So in other words,
and then when the longer you run it, then it would decrease, and you could measure basically how it decreases to achieve some kind of computational randomness. Basically measure pseudo randomness to a computational version of the entropy. Is there something like that?
so if I'm understanding your question right, you're basically asking if there's a way to relate entropy to if there's like a polynomial time function that relates entropy values monotonically to time, and so the longer something goes, the more entropy it has. Is that what you're asking?
Or rather, it would be the other way around, because for the deterministic output, you would expect that the entropy is 0. But but you want to see, okay, if I compute like if I have limited resources, then the entropy would be indistinguishable from a random one. So from that of our truly random source, and then it would be 1. But then as the time increases, basically the value of this computational entropy would decrease to what it is absolutely, like 0. So is there? Yeah. So basically, is there a quantitative version of the entropy, or a computational version of the entropy that can be used for when you have limited computational resources?
Yes. So when you have limited resources, so one, in a sense, when you have limited resources, that is when you would want to deploy something like this already. So that's like one of the motivations. But the other thing too, right, is that doing statistical analysis on low samples introduces much more variance. So you have the potential to both overshoot and undershoot your entropy estimation. And again, like if you were to actually calculate the entropy of the random output from the DRBG at the end of this pipeline, you would be the entropy test calculations would show it to be quite high, even though I understand it's deterministic. The algorithm is deterministic, yes. So it's repeatable. But like just because of all the stuff you're doing in there, like even if it was just hashing alone, that would have a higher entropy value than you might anticipate. And again, because these are all estimations, right? It's really hard to get any true underlying entropy value. But small sample statistics like that can prove to have high variance. So which is why we generally want to have more samples and more data and more time in order to get a better true understanding of the entropy values and distribution of the data.
Yeah, thanks.
Mm-hmm.
There's a question in the chat.
Yeah. So it's leftover hash lemma and minimal entropy. Yep. Have you studied extractors? Yeah, so we've looked at extractors, and this is really cool. So there's a little thing here that I've talked to some of my friends over about, and it's basically this. So an entropy extractor is like a thing that squeezes out all the entropy of it, like almost nothing's left over. So we've talked about the concept of entropy extractors, and basically something that's proven in one of the 90, it's like a 90 suite adjacent paper, it's still NIST, is that, so here's how I think of it, is like entropy is sort of like cannot be changed, the true value at least cannot be changed, but you can change the distribution. So imagine you have a bit stream that has like this as, so you have an entropy value, you have an entropy, you get a number, an entropy is a number, right? So you tack that number on, but the distribution looks like this. It's a little not so uniform. So something that a hashing algorithm has been shown to do in practice is it takes the entropy and it can, so if I put like that, it can like smoothen it out completely flat, but it doesn't fundamentally change how much is there. So hashing is basically like a smoothing function, but it doesn't change the fundamental amount. And so something that some folks at NSA proved, which is really cool, you can read about this too. This is called the discussion on the full entropy assumption in the 90 suite. It's a paper somewhere in the world, which basically says, if you have a target, if let's say your target entropy is H, like you want to reach some amount for some security reason. And then if you just add 64 to that number, then actually it's just as efficient as an entropy extractor. So in other words, you could either choose between this and then use SHA, or you can do an entropy extractor. And ultimately, one of these is in the standard, another is not in the standard. So they pick the one in the standard. I'm sure you can guess which one's in the standard if you know what SHA stands for. Standard hashing algorithm. That's what it stands for. Okay, great. Yeah, happy to yeah, are there any more questions? I'm happy to answer them from people in the audience. And okay, cool. Let me just say one more thing, and this is actually going back to the discussion we had, Francesco. So it's like I'm new in this world, right? I came from FAU. Hi, everybody. But so there are things that I'm learning where it leaves the realm of math entirely. Like there are, when you talk about cryptography, it's a very interesting field. You get into the concept of, are these mathematically secure? Can we implement it in a secure manner? And then will policy allow us to do that? Those are three equally weighted forks in anything in national security or defense. So it's very interesting how you'll have something where you're like, mathematically, this is not secure and you can prove it, but someone with way more stripes on their shoulder and stars on their collarbone, or no, this year, their trapezoid, right here, some stars and stripes will tell you, you must do it this way or else you're in trouble. Or someone might say, the math completely checks out, but I cannot implement this in that way because there's no such thing as a perfect communication channel. Or someone's like, here's the easiest thing to implement, and we have it implemented, and you're like, it's not secure, and they're like, yeah, but every system in the world uses it. So do you want us to reboot every system in the world? Is that what you want us to do? So do you see what I mean? Like, there are things where I hear what you were saying about there's an easy mathematical fix to this. There is not an easy policy fix to it. And all three of those need to be in agreement to get anything pushed up to an official level in the government. So this is why that this was removed.
Okay.
Yeah. But yeah, that's my thought.
I have what is going to be an extremely rudimentary question.
Okay.
I know that there's a way you can use like prime numbers, like for like cryptographic stuff. is the point of like that, to create like a correlation when you're doing like the, handshake essentially between like the sender and receiver? I'm not using the proper terms because I'm a physicist, sorry.
No worries. Could you, oh, I hear you. Yes, this is very good. What I'll say, random numbers are used in key generation. And one of the key generation things that we do all the time is this Diffie-Hellman handshake or RSA handshake.
Yes,
And
that.
right. And those require random numbers more than you might think. So yeah. So like that. So that's absolutely one of the use cases here. That's completely right.
So something that I've been wondering, like it's very, like with our current computers, it's hard to undo that like operation and like invert it to get like the prime numbers which were used, but it's easy to like actually like multiply the prime numbers to begin with. Why do we like need an operation which is like hard to invert in order to like create this correlation essentially?
So imagine, can we like, I want to take one step back. Imagine that I'm like, hey, I've buried secret treasure and it's somewhere in, I don't know, it's somewhere in Florida. You could, in theory, dig every single hole possible in the state of Florida to find it. But if I'm like, here's a treasure map that I secretly, I give to you, then you're like, great, I know exactly where to look. You still have to do it, but you've now reduced the problem space to this one singular like location. That's effectively what cryptography boils down to, is you cannot solve the fundamental thing of like, I want to make a secret channel. But by having the problem where anyone can multiply these numbers, but only someone with a little bit of a hint or a little bit of a cryptographic backdoor or a cryptographic trapdoor, that's the word, a cryptographic trapdoor or a little hint can reverse it to actually get the secret values out of it. That's like giving you the treasure map. That's like, go look in this direction, and then you'll get it way faster than any adversary who's trying to also search for that treasure would. I'm basically giving you a little hint to get to that value that I want to keep secret just between you and me. But I got to like make sure that you can do it.
Okay, I'm just confused why like one-way functions seem to be required for this form of cryptography. Like it's not
How
clear.
else would you keep a secret?
I mean, I'm like I said, I'm a physicist, so I'm
It's
not
okay, yeah.
how all this works really.
It's so cryptographic trapdoors are effectively just used because you fundamentally can't give someone information with nothing. But like that information, theoretically that's not possible. But cryptographic trapdoors allow for someone to invert the locking mechanism you use to safeguard your information. Without a cryptographic trapdoor, that's like having a safe with no keyhole or a safe with no unlocking combination. In a sense, that is the perfect security, but then no one can access it. So you need to have something. If you want this to be sent to somebody and like actually used, they have to have a way to open it. That's what cryptographic trapdoors are. It's a way for the person with the right key, with the right tool, to open up that safe.
But it's not.
Yeah.
Okay, but it's not clear to me why you couldn't like create like a shared bit of private data by sending like information back and forth between the two parties, like which were created was like random data that they generate on their side, pure random data, and like the data that all the data which had been publicly like transmitted like previously in like their own like private data. I don't like see why that's inherently impossible.
It's not impossible, but you have to think adversarially. Imagine someone's on that wire that can hear all of it. Why could they not impersonate one of those two parties?
Oh no, like if they like knew, I mean, I'm like, I know that you could have like an eavesdropper and like they're also getting the publicly sent data, but they don't have like the private data that each party is like generating on their own side. like, if you were not able to impersonate each other for whatever reason, like, is it like definitely like still impossible for like both Alice and Bob to create like shared private data that Eve cannot like figure out based on the information that Alice and Bob were exchanging if one-way functions did not exist?
Maybe we can take this thing offline or something. So
Yeah. I'm happy to talk more. No, it's no problem. But yeah, what I'll just say is the concept of creating shared private information is a very, very important topic in both information theory and also in authentication, because ultimately what you're describing with what you're saying I could pretend with all of Alice's things she's putting public, I can just pretend to be Alice and she's putting it public. I can take it and intercept and say, oh, actually I'm Alice. And then we would create a communication channel between us and you would never know because we didn't do any type of authentication beforehand. So one-way functions provide some level of security where, okay, only you could possibly do this because of the fact that you know this part that like lets you enter that backdoor. So yeah, I'm happy to talk more. Francesco, you have my email, right? My new one.
Yeah.
Yeah, feel free to forward it to anybody who wants to talk more about this, and I can communicate offline if that's okay.
I do. Okay. So thank you very much, Dominic. Yeah. Okay.
Oh yeah, of course, anytime. All right, thank you all.
So it was a very interesting talk, and even the slides are very cool.
Oh, what slides?